I was not recording when I knew you said that. Good times. Okay, so we are talking about vectors today, and there's a relationship between vectors and trigonometry. But fortunately, that relationship is about the law of sines and the law of cosines for the most part. So it's not going to be, this is not difficult. And I want you to know, like, the sheet is going to totally be your friend when we do the quiz on this. Everything you need to know, as long as you understand the notation, it'll be on the sheet. So, I don't know if you need the sheet today. I don't think so. Okay, so we're going to do this lesson over probably 3 days is my guess. So we'll go slow and have small chunks of homework is really what we're looking at. Because we don't have a lot of background with this unless maybe you've taken physics. And my physics knowledge of vectors is not up to snuff. You're getting my sum total of vector knowledge here for the most part. Okay, so a vector, as we know from Despicable Me, is a mathematical quantity. I'm not writing that down. That has both direction and magnitude. Okay, so a vector is a mathematical quantity with both direction and magnitude. Let me give you an example. So you do not have to write this down. But speed, okay, when you start thinking about like driving somewhere, speed is a vector quantity because you're driving in a direction with a speed. So its magnitude would be a speed. So direction and magnitude. Those are real life quantities, are vectors. Now, because we have direction and magnitude, we talk about vectors with more than one number. So they each have like two numbers that we talk about. So a vector would look like this. This is just an example. It can be anywhere in a coordinate plane. So, and then it ends. So it has a little arrow. Okay, I'll zoom that in so you can see it better. There's an arrow with that dot. Why do you think the arrow is important? Yeah, it shows your direction because the arrow could be going the other direction. So the direction, the arrow part does matter. So we call these things, this guy, if this was a P and this was a Q, because I'm just going to give you some labeling here, how people might write it. This guy is called the initial point. Okay, not one word, it just ran together there. And this guy is called the terminal point. We did initial side and terminal side when we were talking about angles, right? So initial just means starting and terminal just means ending. So the way that we would write this, we can name, just like geometry where you can name angles with a letter, you can name angles with 3 letters. Like there's a couple different ways you can name vectors. So you could name it like this, PQ, and to denote that it's a vector, you draw it like this. Okay, but the order matters. The order of the letters matter because you start at P and you end at Q. Because if you put it in the other order, QP, but you kept the arrow the same, that would indicate the other direction. So the arrow, this little half arrow on the top, does make a difference. The other way that we can write it is we can use bold. So they tend to be U's and V's, and they're bold. I don't know how to make it bold when I'm writing in pen, but they tend to be written as bold single letters. Okay, so you can name a vector those two different ways. So, just to make sure that we are on the same page here. let's say that we have let's make this, doesn't really matter. I'll see if I can come up with something catchy, but no. Once you write that, name that vector for me. Just to make sure that we are all speaking the same language here. That you understand what I'm talking about. Okay. What are you naming him? Yeah, he's got to be MT with his line over because he starts at M and ends at T, hence the arrow, right? So MT. If I named him, like I can also, just so you know, again, one more time, if I don't want to write all this crap, I can also name him U as a single bold face. It's just easier to write one letter than it is to write 2 letters and a half arrow. So both of those are possibles. Okay, so one of the things, now that you know this, this is the basic of some vector notation. We would like to, let's talk about how to find magnitude. Okay, and this goes actually on your sheet. So magnitude of a vector, we can write 2 different ways. Nope, we cannot. Looks like this. So it looks like a double absolute value line. So when you see that, that means that you're finding the magnitude of that vector. Okay? And magnitude is just another way of saying the length of the vector. Okay? Magnitude of a vector is the length of the line segment, basically. Okay, so we're going to write the formula down. Okay, on a pink paper, which I think I told you didn't need and I was wrong. Okay, so magnitude of a vector is the square root of delta x squared and delta y squared. And we'll talk about what those are. So if you're like, I don't remember those, it's okay. I'll tell you what they are. Yes.
Seriously?
Yes. Yeah. Yeah. Okay, so this also relates over here to this component form of a vector, which we'll talk about in a minute. So we're going to put delta x is equal to x2 minus x1. And delta y is y2 minus y1. So it's slope related, right? The change in y over the change in x. So not like, we're not talking about rocket science here, Ava. It's just slope that we haven't talked about in a while. So you can, like, we could have written this with the y2 minus y1s, x2 minus x1s in there. But for what's coming, like when we get to this component form, it's easiest to put it like this. Okay, so we're just going to write it like this. So let's say that we have, nope, let's do this. Let's say this is the point 7, 2, and this is the point 12. No, not 12. Let's make him 10. You're welcome. 10, 6. Okay, so 7, 2, and 10, 6. We're going to find his magnitude. So the way that I'm trying, like I'm way zoomed in and I'm having a hard time squeezing it all in. So we're going to find the magnitude of V So, square root. This is really easy. Like, I know it looks like it's not easy, but the formula says change in x. So how much does x change? 3. And then how much does y change? 4. No, it's not. You just gotta, like, there's a lot of notation stuff, but it's not hard math.
So what's the point of having the x and the y in there if you just use the change?
That's what because you have to talk about the fact that it's the change in x and the change in y. Like, do you get what I'm saying? Like, you gotta.
But you don't actually have to write down like the terminal points of x and y, just to change.
Yeah.
Okay.
This what is? I picked this nice for us. What does this equal under the square root? 25. And so what's the square root of 25? 5. That's the magnitude of v. Okay? Which also happens to be how long the line segment is. You guys, this dealie right here is the distance formula from geometry. Sorry, let me find him. There he is. This is a distance formula from geometry, but I know you don't remember the distance formula from geometry. If you cannot remember, it's just the Pythagorean theorem. Okay, so observe, if I had turned this, don't write all over your notes, but if I had turned this into a triangle, okay, how long is this from here, from 7 to 10? 3. How long is this from 2 to 6? 4. And it's just 5, because that's the Pythagorean theorem. It's just rearranged to call it the distance formula. Okay, all Pythagorean theorem related. Anyway, for what it's worth. You're going to have the formula, so it doesn't matter. Okay, so here's an example.
That's good.
Crap. I did not leave myself enough room. That's and. It should be an and. We're not adding anything at this point. Yep. Yep. We're going to talk about what that means. Just give me a second.
Well, they're parallel. Boom. We got the same rate of change. Boom.
Let's go.
We definitely did something like this when I was. They really remember doing something, but they really said.
No. Right.
I remember sleeping in middle school. It's about it. It's about what I do right now.
I remember in middle school, there was a certain you do clacking in your mix so loud.
Camden.
I was gonna say that, yeah. And I told him, I asked him not.
Okay. I'm not drawn to scale here.
Why would I?
No, I screwed something up. Just a second.
What do you do?
Because it was an own.
It's theory of city, that.
This should be. Wow. Just a second. I screwed it up. Okay. There you go. Not drawn to scale. Here we go. So here you go. 2 vectors. This is the definition of equivalent. If 2 vectors are equivalent, they have the same magnitude and they have the same slope. Okay? Same magnitude, same slope. You cannot, listen, if this is the 0.50, you cannot trust this drawing. So you don't know if they're parallel or not.
But they're parallel.
Mm-hmm. I can look at it. Yeah, because 50 is up here. Okay, so listen. You guys, the beauty about slope is change in y over change in x. I'm too zoomed out. There you go. Change in y over change in x. So you got to have change in y over change in x for both of them. So for you, his slope, what's the change in y? 2. What's the change in x? 3. Now, nicely enough, the magnitude of u is going to use those same two numbers, change in y over change in x. You don't have to recalculate. That's really nice. Okay, this does not come out nicely because this is 9 and 4. That's 13. So we're just going to leave them exact. Why would we turn them into a decimal when it doesn't matter? Okay. So go ahead and find the slope and magnitude for v. Okay, so what's the change in y for v? Yep. Also 2 over 3, right? This goes up 2, this goes up 3. So you know that this is going to be the same. Square root of 13.
There's some drama going on.
I can tell. Do you guys have questions about that? I don't feel like I need to do a whole lot more on those. So
Pretty simple.
that part is pretty simple.
I just don't like it wrong. Quiz though.
Okay. So the component form of a vector actually simplifies the way the vectors are. It actually makes less work for us. So it's a little bit of weird looking notation, but it makes life easier. So component form of a vector assumes that the initial point is the origin. Okay, it assumes that the initial point is the origin, which means that life gets a lot easier for us. So let's see. We write component form with these guys right here. These are called angle brackets. So component form of a vector will look like, we're going to write this on our paper also, our pink paper, delta x, comma, delta y. And what this does is it makes it easier for us to add and subtract and do the other things we're going to eventually do with vectors. Okay, so we will work with vectors in component form 9 times out of 10. So I'll show you. I will show you because it sounds like it's terribly confusing and it's actually very easy. So on your pink paper, I want you to put PQ. Okay, and I'm just going to put PQ with the arrow so that you remember that's how you name vectors. Delta x, comma, delta y. And that could also be like a bold case V, or however you want to call it, right? It could be volt. I can change the letters. I can change the letters on the V and the PQ, but it will always be delta x over delta y, or delta x, comma, delta y. So because, listen to the connection. This is why I chose to write these the way we do. If we are dealing with the component form of a vector already, the two numbers that we will see, I'll show you in a second, are already the delta x and the delta y. So it's very easy to find the slope then because it's already there, and it's very easy to find the magnitude because I already have the pieces I need. So let me give you an example. So let's say that we would like to write, 1, 2, 3, 4. I'm not drawing this all. This is 4, -7. 4, -7. And our other point is -1, 5. 1, 2, 3, 4, 5. Okay, and we're going to go this direction. I'm going to go P and Q. And we're going to write PQ. PQ in component form. So I think the thing that's most important when you're doing this is you start, when you're doing the change in Y and the change in X, you start at that initial side. Okay, you're starting at the initial side and seeing what happens. So the change, let's do change in X. So from P to Q, you have to start at the initial side. So from P to Q, what happens? Yes. So when we talk about change in, we go from 4 to -1. That's down 5. Okay. What's delta Y? Nope. This is a 5. So yes, 12. Okay. Because we're going from -7 to +5. Okay. So we're going to, you guys, if you're doing this math in your head, which I totally support, get yourself to 0. That is up 7. So, 7, and then get yourself to 5. That's 12. So the way that we write this literally is just like this. Okay, so this is not, it's not difficult math. It's just understanding what the notation means. Now, watch this. This is why we do it. You don't even have to put this on your paper. But if we see these angle brackets like this, we assume that one point, this is an equivalent vector, one point is at the origin, and the other one is at the point -5, 12. 6, 8, 9, 10, 11, 12. So we would be here. My drawing is not very good, but those are equivalent vectors now. So all we're doing is taking this vector and shifting him so that he's got the same direction and the same magnitude, but he starts at the origin instead. So these little angle brackets are just the indicator that wherever he was shifted. Okay, so my graph, like I said, my graph isn't good. That's why you don't rely on the graphs. But those are equivalent by the numbers. Okay, so let's do another one. So let's say let's say that P is, well, let's do this. Let's say the initial point is -3, 2. And the terminal point is 8, 2. I want you to write him in component form. This one's pretty easy. Takes longer to write it down than it does to do it. What's our first number? 11. What's the second number?
0.
Now, the thing about the thing about this is if two vectors are in component form and somebody says to you, are they equal? This is going to sound dumb coming out of my mouth. Okay. These are two vectors in component form. So let's say we've got 4, 3, and we've got 6, 8. Whoops, sorry. Let's have it. Are they equal? No. If they're in component form, you can look at them and tell if they are equal. Okay, super easy. It's also less work than doing what we did over here, right? Although it's the same amount of work. It's less writing than what we did over here. Because if I was like, hey, this guy in component form would be change in X, that's 3, change in Y, that's 2. This guy is change in X, that's 3, change in Y, that's 2. Way easier than doing all the writing, right? If they are equal in component form, then they are equivalent vectors. So that's just a little bit easier. Okay, so that's all we are talking about today. So I'm going to give you your homework. Just covers what we've talked about today, so it should be pretty easy. I got to get the page number though. 431 maybe. There you go. I'm thinking this should take not very long. No, not an hour.
50 hours.
Connor, you're not going to do it.
Maybe he was probably
That's
Maybe.
that's where you're wrong.
Oh, good.
Aren't you laughing at me?
I'm not laughing at you.
Why? No. Why would you laugh at me?
I'm not laughing at you. I'm laughing at the circumstance.
No, you're laughing at me because I am the circumstance.
No, you're a person, not a circumstance. Don't let
No.
anyone ever tell you anything.
I am a part of the circumstance. Though. Like I am the reason why the circumstance
Yeah,
is
so
there.
is Miss Douglas, so I can do that for my
Well, that's rude. You shouldn't laugh at
There you go.
kids.
I mean, I don't really care.
I felt this afterwards, I didn't do homework in the notes, I don't pause, and then I wake up in the morning in the same position I fell asleep in, and then my body just hurts. I'll get a picture of it.
Got it.
Because I don't take
Wise.
my book home, and